Let's turn from continuous time diagrams to discrete time diagrams. These are a lot more subtle. It's going to require a little bit of work, a little bit of practice to get good at drawing pictures of discrete time dynamics. Now, recall the situation we're in. We're looking at systems of the form Ex equals f of x. And now time is a discrete variable n, and instead of plotting solutions x as a function of time n, what we're going to do is compress out that time variable and focus on the graph of the right-hand side. Let's begin by drawing a graph. Along the horizontal axis, we're going to have x. Along the vertical axis, Ex. I might specify this as xn and xn plus 1 respectively. Now we're going to draw the graph of the right-hand side, this function f. And the first thing we have to notice is, unlike the continuous time case, in discrete time, the equilibria do not happen where this graph intersects the horizontal axis. Oh no, it's where Ex equals x, so it's along the intersection with the diagonal. Now, how do we view the dynamics once we've seen where these equilibria are? Let's choose an initial condition, x naught. That's along the horizontal axis. Now, to get x1, we simply evaluate the function there. Now, x1 is on the vertical axis, but in order to iterate, to keep going, then we need to plug it back in. So I'm going to take that x1, project it back to the x-axis by going to the diagonal and then dropping down. Then we feed x1 into the function. We get the output x2. I'm going to project that back to the diagonal, back to the x-axis. Now feed that back in. That's our x3, and we're going to keep going and going and going. Now this is kind of confusing, lots of points. The way that we're going to make sense of this visually is we're going to draw line segments between xn along the horizontal axis and the point on the graph, which is going to be xn plus 1. Then we're going to make a horizontal line that goes over to the diagonal and then feed that point back into the function, drawing a vertical line. So vertical, horizontal, vertical, horizontal, vertical, horizontal, keep going, keep going. This is going to give you a picture of what an individual initial condition does. And now you could start doing some interesting things like moving that initial condition back and forth and seeing what happens to the associated dynamics as you change the initial condition. We can see how equilibria can be stable. We can see how equilibria can be unstable, where you're moving away from it. That's all really cool. Now let's take a moment and talk about notation. This is often called a cobweb diagram. Bad name, awful name. We are not using that name. No, look, it's just a diagram. There's no need to come up with fancy names for things. Now, let's get back to the problem at hand. Can we see what linearization means? Can we see the details of the stability criterion emerge? It's a little bit harder in this case. Let's focus on what is happening in a neighborhood of an equilibrium, where the graph of that function f is approximately a straight line. That's what linearization means. And then when the slope of this graph is less than 1, you can see, drawing that diagram, that we're just bouncing around, going straight into that equilibrium. Now, what's interesting is the difference between a positive slope and a negative slope. As long as it's less than 1 in absolute value, you are converging into that equilibrium, either directly or in an alternating fashion. Contrast that with what happens when the slope is bigger than 1 in absolute value, in which case you are rapidly getting pushed away. With a little bit of thought, we can even make sense of degenerate equilibria, just like we did in continuous time. Consider the case where the derivative is equal to 1 at an equilibrium. This can happen in a couple of different ways and can involve a sort of mixture of stabilities, or a very, very slow approach into an equilibrium. Things like that can happen. It's a little weirder when that slope is equal to -1. It's as if you're bouncing around and you're not really sure. You can't really make up your mind. You're going to converge or not. It's really, really slow. It's a higher order phenomenon. These diagrams, these discrete time diagrams, are worth your attention, but you have to be careful. These are not as straightforward as their continuous time analogs. It takes a little bit of practice to get good at drawing these and interpreting them. But don't worry, we'll get some practice.